In this session, we will try to understand a couple of the topics, and the first one is the working of BJT in active region. Earlier I explained that BJT can be operated in one of the three regions. The three operating regions of BJT are active region, saturation region, and cutoff region. So, what is the condition to operate BJT in active region? The biasing between the emitter base and the collector terminal decides operating region of transistor. In this figure, you can see that emitter base junction is forward biased and base collector junction is reverse biased. That means on the left side between base and emitter terminal, we have the source VEE, where the negative terminal of VEE is connected to emitter and positive terminal of VEE is connected to the base terminal. And on the right side between base and collector terminal, we have the supply VCC. VCC is connected between base and collector in a such a way that this base collector junction comes into the reverse bias condition. So when we provide such type of supply to BJT, the BJT works in the active region. What happens inside the BJT while we bias the emitter base junction with the VEE and base collector junction with the VCC? Inside the BJT, the heavily doped emitter injects its free electrons into the base. So we know that because emitter region is the N-type material, the majority carrier inside the emitter region is electrons. So most of the electrons from the emitter cross this base emitter junction and enters into the base region, which is the P layer region. And from the construction point of view, we understood that this base region is lightly doped region, right? Compared to emitter and collector, the doping level of the P region, I mean to say base region is very less. So because of that, whatever the electrons come into the base region from the emitter region would diffuse to the collector region. The collector, the task of the collector region is to gather most of the electrons from the base region. So thus, here you can see inside the diagram that flow of the electrons from emitter region to the collector region through the base region. So majority carrier inside the electrons cross the emitter base junction because of the forward bias condition is placed via this VEE supply, and because the base region has very less doping, most of the electrons do not get chance to recombine with the holes of this base region, and hence the electron will pass this base collector junction from base to collector region, and these electrons flow through the collector and through RC into the positive terminal of this VCC voltage source. So that is shown by these arrows. You can see that the electrons come out from this collector region, passes through this RC, that is the collector resistor connected to the collector terminal, and reaches to the VCC supply. Right? So this is how the movement of the majority carriers takes place inside the BJT when we provide supply VEE and VCC as shown in the figure. Now let us understand a couple of the terminologies regarding this operation. The first is the emitter efficiency. It is also termed as emitter injection ratio. What does it mean? It is defined as the ratio of charge carriers injected by emitter into the base to the total emitter current. Right? Total emitter current means the emitter current which is made up of both type of carriers, minority carrier as well as the majority carrier. In this NPN type transistor, the emitter region is made up of N type layer, and because of that, majority carrier for emitter region is the electron. So the current due to this movement of electron is INE, and this emitter region has minority carrier holes, and because of movement of the hole, the current resulted is referred as IPE. So the total emitter current is given by INE plus IPE. But during this active region operation, what has been injected from emitter into the base because of these VEE biasing majority carriers, and the majority carriers are electrons, right? So current due to injection of electrons from emitter to the base region, that is INE over here, and the net emitter current is IE. So the ratio of these two current is known as emitter efficiency, that is emitter injection ratio. Normally, how do we calculate efficiency? Efficiency, the general formula of efficiency is output divided by input. Here output is total number of the majority carriers injected by electron into the base, and the input is the total emitter current which is due to minority carrier as well as the majority carrier. So this is emitter efficiency. Moving ahead, a typical value of gamma. It is the notation used to define this emitter efficiency is gamma, and typical value of gamma is 0.995, 995, right? Obviously, these value can be understood from this formula that INE divided by INE plus IPE. So the magnitude of INE is greater than magnitude of IPE. What is IPE? That is current due to minority carrier. And what is INE? That is current due to majority carrier. So when we take the ratio of these two quantities, INE and IE, the most of the time we get the value greater than 0.99. Let us go through the another terminology, that is base transportation factor. It is defined by beta. Here the notation used is beta. So what is this base transportation factor? Again, it is a ratio between two currents. The first current is INC and the second current is INE. What is INC and what is INE? So first of all, let us go through the statement of this terminology, that is definition of this terminology. It is defined as the ratio of charge carriers arriving at the collector. Arriving at the collector means the number of the majority carriers arrived at the collector to the number of emitted charge carriers. That means number of the charge carriers injected by emitter. Right? For example, 100 majority carriers are injected by emitter from emitter region into the base region. Out of 100 carriers, 5 carriers recombine with the holes inside the base region for a short period of the time, and rest 95 carriers cross this base collector region and reaches at the collector region. Whatever the majority carriers arrived at the collector region, that constitute collector current IC, and after a short period of the time, the recombination of the electron holes breaks due to this positive biasing of the base terminal, and those 5 electrons passes through this base region and the base terminal, and it goes to the VEE source. So these 100 majority carriers are divided into two parts. The first part is 5, that is uh, 5 majority carriers stay while inside the base region, and 95 carriers reach to the collector region. So this base transportation factor defines the number of carriers received by this collector divided by number of the carriers injected by the emitter, that is INC and INE. So typical value of the beta is 0.995, right? As I said that most of the majority carriers uh, goes to the collector region, and very few electrons stay for a while inside the base region before they move to the VEE, to the base terminal. So the base transportation factor beta, the value of the beta is typically 0.995, and it is defined as INC divided by INP. Then next terminology is the large signal current gain, which is denoted by alpha. So for NPN transistor, the total emitter current is due to emitted electrons INE as well as due to the minority charge carrier holes IPE. Right? So IE emitter current is made up of these two types of carriers, majority carrier electrons and the minority carrier holes. So by keeping that information into mind, let us define large signal current gain alpha. So it is the ratio between increment in the collector current, which is IC minus ICBO, where ICBO is collector to the base leakage current when the emitter is open. Right? What is IC minus ICBO? IC minus ICBO is the current flowing between collector and the base terminal when the emitter is open. The emitter is open is referred as when there is no biasing between emitter and the base region. That means this VEE is not present. Due to only this VCC, due to the presence of VCC, the current flow between these base and collector terminal, that is known as IC minus ICBO. And what is ICBO? ICBO is the flow of minority carriers between base and collector terminal, right? So the large signal current gain is the ratio between this collector current increment and total emitter current. What is total emitter current? That is due to majority carriers electron and the minority carrier holes, IE. And what is collector current increment? That is INC. That is IC minus ICBO. So this is about large signal current gain alpha, and typical value of the alpha is in the range of 0.9 to 0.995. Now let us go through the different current components. Because the transistor is a three-terminal device, obviously there has to be at least three currents. Each current is corresponding to each terminal. So when the transistor is of NPN type, then the conventional direction of the current are shown here in the diagram. IC, sorry, IC, IB, and IE. And when the transistor is of PNP type, then the direction of the current IC, IB, and IE are shown here. As the emitter is the source of the electrons, it has the largest current, obviously, because movement of the majority carrier starts from the emitter region, right? So out of these three currents, the magnitude of emitter current is always higher than the base current and the collector current. Since the most of the emitter electrons flow to the the collector current is amongst the as large as the emitter current, right? As we have seen earlier in this session, when we operate BJT into the active region, most of the majority carrier which are emitted by emitter region goes to the collector region, and because of that the magnitude of the collector current is also high, nearly about emitter current, magnitude of the emitter current. The base current is very small in comparison to collector and the emitter region, often less than 1% of the collector current, right? Because the area wise as well as the doping point of view, the base region is small, so the current corresponding to the base terminal is always less, and it is approximately 1% of the collector current. So out of these three current, emitter current is the highest and the base current is the lowest, and the magnitude of the collector current is near about the emitter current, but not exactly same as the emitter current. Sometimes we may take into consideration that collector current is approximately same as the emitter current. That you will see in the subsequent theory in subsequent slides, right? So relation of the currents. So what is the relation among these three currents? So from the operation, we can make this equation that ammeter current is nothing but the summation of other two current, that is base current and collector current, right? So as per Kirchhoff's current law, it says that the sum of all currents into a point or the junction equals the sum of all currents out of the point or junction. Emitter is injecting the carriers, base region collects few of the majority carriers, and rest of the majority carriers are collected by the collector. So total emitted carriers is equal to carriers collected by base region and the carriers collected by the collector region. So IE is equal to IB plus IC. As discussed earlier, that sometimes we may take this approximation between these two current, that is collected in the ammeter, because base current is very small due to light doping as well as the area of the base region is small. So the collector current approximately equals to the emitter current. But base current is very less than the collector current, right? In the previous slide, uh, the point was given that the magnitude of the base current is approximately 1% of the collector current. So you can see that the magnitude of the base current is very less compared to the collector current. The next point is the current gain transistor. Current gain in the transistor. So let us discuss various gain in the transistor. What is gain? Gain is nothing but it is one type of ratio. So let us first of all discuss the current gain, which is denoted by alpha DC, and we go through the definition of alpha DC. What is alpha DC? Alpha DC is the ratio of collector current to the emitter current. That means output current divided by input current, right? In the previous case, our input current is emitter current and the output current is the collector current. So output divided by input. This ratio is of the current parameter. Because of that, it is known as the current gain and it is denoted by alpha DC. Since the collector current almost equals the emitter current, the DC alpha, or you can say the current gain alpha, is slightly less than 1. Right? If we think that IC is exactly same as the IE, then we can substitute IE here. So IE divided by IE, that is equal to 1. That is the maximum value of the current gain. But in practical, the magnitude of the IC is slightly less than IE. So when we solve this ratio, then the magnitude of alpha DC is typically near to 1, right? It should be near to 1. So the DC alpha is typically greater than 0.99. That is the typical value. So even in a high power transistor, the DC alpha is typically greater than 0.95. What is high power transistor? Uh, Transistor is also classified based on the power level. The transistor which we normally see in the laboratory, that is a low power transistor, but in real-time application where high power applications are implemented, there we need high power transistor which can handle higher magnitude of voltage and higher magnitude of the current. So in high power transistor, the typical value of alpha DC is 0.95. Right? So next gain in the transistor, next current gain in the transistor is the beta. Again, beta is also the ratio between the two currents. The first current is the collector current and the second current is the base current, right? You can see that collector is the output current and the base is the input current. For base collector junction, where VCC supplies given between the base and the collector region, right? So it is defined as the ratio of the DC collector current to the DC base current. When the DC biasing is applied between the base and the collector terminal, at that time the output current is the collector and the input current is the base current. So ratio between these two current is known as the current gain beta. A small base current controls a much larger collector current. We know that magnitude of the base current is very less compared to the IC. The current gain is the major advantage of the transistor and has led to all kinds of the application. This gain is the responsible for transistor being used as an amplifier. For low power transistor, which can be used under 1 volt, the current gain is typically 100 to 300. And for the higher power transistor, which are being used over 1 volt application, usually have current gains of 20 to 100. These are the typical values of beta DC for the lower power transistor and the higher power transistors respectively. Let us build up the relation between these current gain alpha DC and the current gain beta DC. So to build up the relation between these two, we must have idea about the basic equation of the transistor, that is IE is equal to IB plus IC, that is emitter current is made up of base current and the collector current, that is this one, right? So when we divide this equation, when we divide this equation by IC on both sides, on the left hand side as well as on the right hand side, uh, we get on the left hand side IE divided by IC, and on the right hand side we get IB divided by IC when the base current is divided by IC, and when the collector current is divided by IC we get IC divided by IC, right? So when the first equation, that is this one, when this equation is divided by IC on the both side, we get the second equation, right? But from the definition of alpha and beta, we can convert the second equation into this one. IC, we understood that IC divided by IE, that is alpha DC. So we can substitute alpha DC in the denominator on the left hand side. And from the previous discussion, from the beta DC definition, we understood beta DC is the ratio of IC and IB. So on the right hand side, we have in the denominator of the first term as beta DC, and what is IC by IC? That is equal to 1. So by simplifying this equation, we can have 1 upon alpha DC on the right hand side and on the so on the left hand side, and on the right hand side by taking beta DC as LCM to get 1 plus beta DC divided by beta DC. So by inverting this equation on the both side, we get alpha DC is equal to beta DC divided by 1 plus beta DC, right? So here we can say that current gain alpha DC in terms of current gain beta DC. But sometimes we need beta DC in terms of alpha DC. So how to do that? This can be done from this step onwards, right? So from this step, we can write this one by making 1 divided by beta DC as a subject of equation. So when we sign this 1 on the left hand side, the equation results into 1 divided by beta DC is equal to 1 upon alpha DC minus 1. By taking LCM on the right hand side, we get 1 minus alpha DC divided by alpha DC. And finally inverting the terms on the both sides, we get beta DC as alpha DC divided by 1 minus alpha DC. That is current gain beta in terms of alpha, right? This DC in suffix of beta and in suffix of alpha defines these two current gains of the transistor when the transistor is biased with the DC supply. Now let us understand the types of transistor configuration. We know that transistor has 3 terminals, that is emitter, base and the collector, right? But to connect a transistor in a circuit, we need 4 terminals. Even number of terminals are required when we want to connect transistor in any circuit diagram, right? And basically 4 terminals are required. Why 4 terminals? Because 2 terminals should behave as input terminals and 2 terminals should behave as output terminals. So here you can see that 2-port network system where input port has 2 terminals and output port has 2 terminals. But in transistor we have 3 terminals. So how can we get 4 terminals while connecting transistor into any circuit diagram? Very simple. Out of these 3 terminals, 1 terminal can be made common between input and output. So if one of the three terminal is used as a common to both input and output, then the transistor can be considered as a two-port network. So here you can see that the first terminal, second terminal, and the third terminal is made common between input and output. So the third terminal is connected to the input side as well as the output side. This is how we can create four terminals, and we can connect transistor into any electronic circuit. So which terminal is made common between input and output? Based on that, we have three configuration. If emitter is the input terminal and collector is the output terminal. So here in the diagram, you can see that emitter is the input, collector is the output. So the remaining base terminal is made common between input and output. So the base terminal can be considered here as one of the input terminal as well as one of the output terminal. So input is given between the emitter and the base terminal, and output is taken between the collector and the base terminal. So here the base terminal is the common between input and output. Because of that, this configuration is known as the common base configuration. Similarly, if emitter terminal is the common between input and output, so here input is the base terminal, output is the collector terminal, and emitter is made common between input and output. That means input is given between the base and the emitter terminal, and output is taken between the collector and emitter terminal. So here emitter is made common between input and output, between base and collector. So this configuration is known as the common emitter configuration, where the emitter terminal is made common. And when the collector terminal is made common between base as input and emitter as output, then the configuration is known as the common collector configuration. So in the diagram, you can see that input can be given between base and the collector, and the output is taken between the emitter and the collector. So this behaves as an input port, and this behaves as an output port in the two-port configuration. So these are the three configuration of the BJT. The first is common base, second is the common emitter, and the third is the common collector. Right? So let us see the diagram of common base configuration. Right? So here you can see that the transistor is horizontally aligned. Horizontally aligned, that means you can see that emitter terminal is this one, collector terminal which should work as an output terminal is this way, and the base terminal which should behave as an input as well as the output in this way. Right, so alignment of the transistor is horizontal rather than the vertical. Horizontal means it is placed in this direction. Right, so emitter terminal is connected to the battery VEE, DC supply VEE, through the RE, that is emitter resistor. It is the current limiting resistor for the emitter terminal, and collector terminal of the transistor is connected to the VCC through RC, that is current limiting resistor, collector resistor RC. Right, so emitter base junction is the forward bias, and CB, that is collector base junction, is the reverse bias. So here the active region biasing is shown. Right, operation of the BJT, whether it works in the active region, whether it works in the saturation region or the cutoff region, is decided based on how you bias these three terminals of the transistor. Right, that means when you apply the DC supply between these terminals, emitter base and the base collector, that decides the operation of the BJT. active region, saturation region, and the cutoff region. So to forward bias EB junction, VEE battery is connected, and to reverse bias CB junction, VCC battery is connected. And as I said, RE and RC, these two are the current limiting resistors, right? So this is about the common base configuration and its connection. Current gain alpha DC, right? So previously we discussed current gain alpha and current gain beta in terms of general, but now this current gain alpha DC is for this common base configuration. Similarly, we will derive the equation of current gain alpha DC for common emitter as well as the common collector. Same way, we will go for the derivation of beta DC for each of these configurations, that is for common base, common collector, and the common emitter. Right? The reason for having current gain for each of the configuration is in each of the configuration, the input terminal, output terminal, and the common terminal are different. So our output quantity, input quantity may get changed. So for this common base configuration, the current gain alpha DC is nothing but is the ratio of collector current and the emitter current, where emitter as the input in this configuration and the collector is the output terminal. In the common base, the base is made common between input and the output. So current gain, that is output current divided by input current. And as I said earlier, ICBO is nothing but it's a reverse leakage current between the collector and base when the emitter is open, right? And the magnitude of ICBO is very small, so sometimes we can neglect ICBO and we can have the approximation for alpha DC, that is alpha DC is nothing but the IC divided by IE, right? So collector current is equal to alpha DC into IE plus ICBO, right? That is derived from this equation by making IC as a subject of equation. So when I send the denominator IE on the left hand side, so it gets multiplied with alpha DC. So IE into alpha DC, and when I send this ICBO on the left hand side, it becomes plus, and on the right hand side only IC remains. So collector current IC in terms of alpha can be represented as IC is equal to alpha DC into IE plus ICBO. So for the common base configuration, IE is nothing but IC plus IB, and from the first equation, I can write IB is equal to IE minus IC, that is rearranging this term by making IB as a subject of equation into this one, right, into this one, and by sending IC on the left hand side, we get IB is equal to IE minus IC, right? But in the previous slide, we derived IC in terms of alpha DC as this equation, alpha DC into IE plus ICBO. So when we substitute this IC into this equation over here, the resultant equation we get is IB is equal to where IE minus alpha DC into IE, and because of this minus, this ICBO also gets minus. It becomes negative, right? And in this equation, In the first two term, IE is common, so we can take it outside. So IE inside the bracket 1 minus alpha DC minus ICBO. As discussed earlier, ICBO, the magnitude of the ICBO is very less because it is due to the movement of minority carriers, and it is the leakage current. So we may neglect ICBO. So when we neglect ICBO, the equation of the IB can be approximated as IB is equal to IE inside the bracket 1 minus alpha DC. So this relation among the currents will help us to solve few numericals, and that uh, also may help us to design specific parameters uh, for the circuit. Input characteristic of CB, when the transistor is in the common base configuration, when the transistor is connected in the circuit diagram in the common base configuration, at that time input parameters are emitter current and the base voltage, base emitter voltage. So what is input characteristic? Input characteristic of CB is the relation between the transistor input current IE and the input voltage VBE, right? When we want to operate BJT into the active region, this base emitter junction is forward biased via this VEE supply, and because of that, the base region and the emitter region, base emitter base region combination behaves as a diode. So the input characteristic of BJT when we use the common base configuration results similar to the diode characteristic, that is voltage applied between anode and cathode versus current through passes through the diode, right? So the input characteristic of CB is similar to the diode characteristic. The reason is that the first junction, base emitter junction, is in the forward bias condition, right?